Okay, so I saved the best for the last. So I'll play the devil's advocate. So you have seen a lot of positive results out of machine learning force fields, right? I think people try to present the best things they could do with the different force fields, including maze, grace, and solar, and so on. But I now would like to actually go a bit into what needs to be done in the future. So I think the best scientific breakthroughs are the ones that open doors and not close doors, right? And I do think that machine learning force fields have opened a lot of doors. And some of those doors are very positive, right? But some of them, open many challenges that we will have to deal with in the future. And I thought it's something that we are, of course, discovering as we go. Right? Usually, doing applications is very nice, right? Because you can actually discover things that don't work. Right? So I think addressing things that don't work is much more exciting than addressing things that do work. By basically doing all these different applications to material science, chemistry, biology, and in general complex systems, we realize a lot of things that don't actually work in machine learning force fields. And some of the lessons that you will see are sort of lessons that people already learned in classical force fields, right? I mean, we had a ICQC conference, which is one of the biggest theoretical chemistry conferences in Berkeley just a few weeks ago, and there was a special workshop on machine learning force fields, and some of the people that were here also were there. Gabor Chani was there, and everyone was just talking about long-range electrostatics, right? And I think if you ask people from the classical force field community, they will just laugh at this, right? Because they solved classical electrostatics, 40 years ago, right? While we are still discussing about incorporating long-range electrostatics in our force fields, right? It's a bit comical, right? In the sense that, everyone knows that long-range electrostatic is important, actually, or many people know. But in this community, people are just discovering this, right? So that's fine, right? This happens. But there's many other challenges, and of course I cannot mention all of them, but I will show some of them that we have discovered in the group, and I think that resonate also a lot with the other talks that you had during the first day. Okay, but of course, let me remind you, you've seen this nice picture many times, and our general goal as well, just to repeat this, is to go towards more general quantum accurate force fields. And of course, that means really connecting again between the two famous Nobel Prizes in our field, and we want to push this arrow, right, that you've seen, the present in 2021, we want to push it to the right and try to study as complex systems as actually possible, so that we can revolutionize understanding of structures, properties, and function of complex materials and biological systems, or materials in general. Now, of course, all this really relies on data sets, and you've seen this. I don't want to repeat this, but I would just like to say that we are not yet done, right, with constructing data sets. In fact, what we have done really well, I think, both us and Meta and other people, is basically trying to construct structures of different systems that are very useful in these campaigns of creating quantum accurate data. But of course, this data has pitfalls, right? We are using density functional theory, which, as you know, is approximate. And for example, the QCell paper, not just the QCell data set, so the QCell paper actually summarized all the different data sets which were computed at the PBE0 plus MBD or MBD-ML level of theory. And you see it here, for example, the QM7X, QCML, AQM, GEMS data set, and so on. They now cover about 40 million molecular structures. But of course, as you all know, MBD, for example, is a very good theory for long-range interactions, but PBE0, of course, is a very nice functional, it's a non-empirical functional, but it has issues. For example, even if you take a water dimer, you compute it using PBE0, even without including van der Waals interactions, it will overestimate the hydrogen bond. Right? If you take formic acid dimer, that's the worst case, because the stronger the hydrogen bond, the more the overestimation, because your electron density overpolarizes, and this has to do with self-interaction errors. The same thing happens if you have a large molecule, which is aromatic usually, and you do torsions. Basically, you can have charge transfer, right, which is wrong because the homo-LUMO alignment of the molecule is actually wrongly described. Again, has to do with self-interaction errors. And so this, I would say, is probably the biggest problem, this overpolarization and the treatment of homo-LUMO sort of charge transfer effects are the biggest problems for hybrid functions. Now, on the other hand, of course, you have the OMOL dataset. Now, the OMOL dataset uses the omega B97M functional with VV10 dispersion, and it has better chemistry, right? Because it was fitted explicitly to reproduce good chemistry. So there was a large number of coupled cluster and other calculations used to actually fit the parameters in the omega B97 M functional. Right? It has 40, 50, whatever parameters. I don't like empirical functionals, right, by myself, but of course, if you fit it to accurate data for small molecules, well, you reproduce them better. So let's say it has good chemistry, right? Better chemistry than PBE0, definitely, but it's completely inadequate for long-range physics. So the VV10 functional scales really, really badly the system size. And it's actually very unfortunate, and we agree on this with Gabor as well. It's very unfortunate that Meta didn't think of separating dispersion interactions from the parent function. Right? If they did, this data set would be much more useful to the people. So the only useful part of the OMOL data set are really small molecules, right? You shouldn't be using the data for large molecules from this data set because the dispersion interactions are highly overestimated and it's not really scalable, basically, right? So for that reason, we actually do use part of the OMOL dataset in the construction of Solar version 2 that Adil talked about, because I do think it brings in better chemistry, right? Although I'm still quite allergic to empirical functionals, but nevertheless, it's really nice to have this data. And I think the next step is pretty clear, right? The next step is having coupled cluster data. And of course, we are working on that, and I think also other people are working on that. And in fact, today, it barely becomes possible to produce enough coupled cluster data for small molecules. Okay, then of course, once we have the data, we come to the model, and you've heard a lot about different models, but I would just like to show, that our Solar construction would be perhaps the most complete model out of all machine learning, general purpose machine learning force fields that exist. As I will show in the next few slides with the challenges, right? At the moment, we don't have a good model for long-range interaction. So Gabor nicely discussed in his talk the ACE construction, then the need for message passing, because ACE is not scalable, right? So it's only good for short-range interactions. Then you need message passing to extend the range. But this is not all, you are not done yet, right? There are interactions at much higher scale. So message passing is not enough. And in order to really cover long-range interactions, you actually need a multi-scale architecture that propagates environments, right, in a multi-scale manner. And this is what we have actually done. We have a preprint on this with Alex, who is in the audience, Alex Solle from Barcelona. And we demonstrate what is the next step, right? And several other people are working on sort of extending the range of machine learning force fields, and we are not done yet. There's next breakthroughs that must come in order to really treat multi-scale interactions, right? The architectures are not converged yet, okay? But what is clear now, right, assuming we don't yet have the final multi-scale architecture, is that we need to include long-range interactions explicitly. So many people said, for example, if you look at the UMA model, right, it doesn't use any long-range interactions. I think it's pretty bad because it's not a scalable model. And if you look both at our developments and also at MACE, slowly, people are incorporating long-range interactions explicitly, okay? And so I think we all agree by now that we need short-range repulsion because we don't want to learn the repulsive potential. It doesn't make any sense. We know the physics there correctly. So there are several versions of the repulsive potential. We do need a neural network, covariant graph neural network for semi-local interactions because we have absolutely no idea how to analytically describe chemical bonds. I think we all converged on that as well. And we use, all of us are using message passing and some equivariant atom local, semi-local representation around every atom. And then the questionable part, which I think, as I said, for the moment, we all agree on, is that we do need to include long-range interactions for accurate simulations. And so usually people started to include electrostatics. But electrostatic is not the only long-range interaction. There is dispersion, there's polarization, and there's all different couplings between these different effects, which we are not yet addressing, right? So this is all still approximate because we use pairwise, usually atom pairwise representations for these interactions, and this is not the whole story, okay? And we have published many papers, and we have a few preprints also together with Adil, where we actually show how interactions actually decay in real molecular systems as you scale their size, and that demonstrates that we are not yet done really in constructing the right architecture for long-range interactions. But you know, we've done a good job already up to say 10, 20 angstrom separations. Okay, so we've tried to sort of in a group to summarize the different successes and the different challenges, and as I said, I will be the devil's advocate here, so I would claim that our successes are actually very restricted still, and there are many more challenges, right, to go really beyond and enable fully quantum aware machine learning force fields that are scalable across all states of matter. So I think some of the great successes is describing liquids, right? Solvent densities. Florian showed you these results. There is also the papers from Gabor's group on this. I think this is really fantastic. We are very predictive for certain solvent properties. Not all of them. Diffusion coefficients are still problematic. This might have to do with long-range interactions, with quantum nuclear effects, and so on. But overall, I would say it's amazing that we can do better than empirical force fields, which are explicitly fitted to experimental data. We have not fitted to any experimental data, right? We are doing everything from first principles, and yet we can be better than those empirical methods. To me, this is really an amazing fact. Now, you have seen from Miguel's talk that sometimes chemical reactions magically work, right? I mean, we don't have any chemical reaction data in our data sets, but we do have very distorted molecules, and that seems to be enough to actually do a lot of chemical reactivity. This is really mind-boggling, right? Because Miguel, when he came to the group, he said, solar will not work for my reactions. And then suddenly, right, he does, you saw it in his talk, they work really, really well, right? Same for Evgeny's work, right? Reactivity in solvents, it actually works really well, and sometimes it can be predictive, right, of experiment. So to me, these are amazing successes. Spectroscopy is also an amazing success, right? Spectroscopic properties, you know, solvotochromic shifts, they also all work out of the box, because now machine learning force fields allow you to include conformational degrees of freedom, but also varying electric fields. And this is what classical force fields could not do, right? Our electric fields, our charges, right, or dipoles, they actually evolve with the conformation of the molecule, and this enables you to do a completely new level of simulations and properties that you were not able to do before. But it's pretty clear, right? So even if you look at water, right, liquid water, many current general purpose machine force fields get it completely wrong. If you train on PBE0 plus MBT data, you overstructure. If you train on OMOL data, you understructure, right? And even, you know, getting the RDF and the density of water actually seems to be a problem, right? So this is not okay, right? We need to go beyond this, and there are several ways to do that, but this is still an unsolved problem, even liquid water, right? I mean, water is not a simple system, right? People have studied it for more than 60 years, probably, with molecular simulations, and we are not done yet. You clearly need beyond DFT data, as I already said, and there are several efforts now being undertaken towards that regard. Heterogeneous systems, like a molecule on graphene, or molecules on surfaces, are still problematic. You have many different degrees of freedom, and you could have carbon atoms in graphene and carbon atoms in your molecule, which are actually described with different accuracy in your machine learning force field, and that will have implications for the dynamical behavior of these molecules. Your overall error, right? We are optimizing the loss function on forces, but the force errors on the molecule, on the carbon atoms on the molecule, can be much larger, an order of magnitude larger than in graphene. Your overall error will be very low, right? Because it's dominated by graphene. Your graphene is perfect, but your molecule is not. And so then you will get errors in the dynamics. You have to basically flatten your errors. You have to make sure that all your carbon atoms are correctly described, and not just the carbon atoms that are dominant in graphene. I will show you some examples where, in terms of interaction, this is Hessian matrices here, and you show how a machine learning model in green behaves in a completely different way than the reference DFT calculations, okay? So these are long-range effects, and one way to benchmark them is through Hessian matrices, okay? And of course, we've discussed uncertainty estimates, And the final dream is really to do all states of matter, right? You do from a gas phase water molecule to water clusters, to a liquid, to ice, right? To water surfaces, and anything else, right? And ions in water, right? You want to do all states of matter with a single model. We are not there yet, but that's the dream. Okay, first of all, so yes, sometimes general purpose machine learning force fields can actually be consistent. So here's some data, comparison to experimental vibrational spectrum for a bunch of molecules. There are two different data sets. In experiment, there's high trend data set for 22 molecules, and there's NIST data set for 122 molecules. So this is experimental data for vibrational spectrum of small molecules. And here you can actually do harmonic approximation of molecular dynamics using PB0 plus MBT, using omega B97 MV, right? You see, first of all, that in a harmonic approximation, these two functionals are pretty consistent to experimental data, right? There's absolutely, I mean, there's some differences between them, but in terms of the Pearson R coefficient, right, they are pretty much consistent, right? So this is nice, there's consistency between these two functionals, which means that you also expect consistency between the general purpose machine learning force fields. And in fact, you get it, right? So here is solar, here is AIMNet, here is Maze Polar, here is classical force fields, they are much worse, okay? So this is a big progress, right? Compared to classical force fields, just doing harmonic approximation, doing molecular dynamics, our general purpose machine learning force fields are first of all consistent between them, and second of all, they are actually quite accurate, okay? Now, another thing which is interesting, if you can run molecular dynamics, you see you get much of an increase in the correlation coefficient, right? So in solar, which is the only method here that you can actually run molecular dynamics on all of these molecules because it's efficient, computationally efficient, you get actually a bump of coefficient from 0.6 to 0.74, right? So it means that if you increase a bit here, right, you can get to about R of about 0.8, 0.85, which is pretty close to experiment. Right, and of course, if you include nuclear quantum effects and so on, this will even go up, right? So this is really a success, and this shows how, in terms of vibrational properties, machine learning force fields, general purpose machine learning force fields, can be very consistent. But of course, already, you know, in 2022, 2023, actually even earlier, I think this paper is 2018, I think. Yeah, for 2018, we have already demonstrated if you take a molecule like aspirin, right, then if you construct a machine learning force field based on coupled cluster and DFT, you get completely different free energy surface profiles, right? So this is simple molecule, it's aspirin, right? But aspirin has different torsion angles and it's prone to charge delocalization error, and that's why DFT sometimes can predict free energy surfaces which are very different, and this of course has implications, for example, for vibrational spectroscopy as well. So DFT can have errors by itself, and so you need to be careful, and sometimes you need to go beyond DFT, right? So this just confirms that what we observe for single molecules, of course, also applies for large chemical spaces. The second thing is how transferable our machine learning force fields are, right? So one thing you can do, I mean, first of all, you cannot analyze machine learning force fields as simply as you analyze classical force fields. So in the domain of classical force fields, you would define atom types according to bond orders, right? So you could have an sp, sp2, sp3 bonded carbons. You can have different environments for a carbon atom. And if you look at something like GAF, right, the amber, the general amber force field, it would have, I don't know, 10, 20 atom types for each carbon. You can introduce many more, right? But usually you don't want to do this. So in a machine learning force field, we have a much more delicate, subtle situation, because what we do is we train on many different configurations of molecules, which can be close to equilibrium or out of equilibrium. So for example, you could have a situation where your hydrogen atom can undergo proton transfer, and that is in your data, right? And so what is that hydrogen atom? At one point it's bonded to carbon, at another point it's bonded to nitrogen, but it also can be somewhere in the middle, right? Which means that just chemical environment, right, so needs to be upgraded, right? You cannot just use bond order as an indicator for basically the environment of an atom, right? And of course you could say, well, I do angular momentum expansions, right? And I define some index for my environment, but we decided to do more, sort of a more physically inspired approach, which was done by Anton, which we call orbits. So orbits are basically persistent subgraphs of a molecular graph. So you take all molecular graphs in your data set, you then obtain persistent subgraphs that exist there for each element, carbon, nitrogen, hydrogen, oxygen, and then it allows you to define basically an index, right? And so if you take the data set that was used to train Solar, version 1, then you realize that, for example, you have 72 different hydrogen atoms, or hydrogen orbits, okay? So this had 72 different environments for hydrogen atoms, right? So it's just many more than what you have in a classical force field, right? Classical force field, you maybe will have 3 or 4, right? Here you have 72 because it's an unbiased, basically, analysis of all the different subgraphs that hydrogen exists in, right? For carbon, you would have 225, right? Carbon is very flexible in the bonding patterns, so you can have a lot of them. And then what you can do is once you have this indexation, right? So you have an index for each atom, for each element, you can basically analyze how accurate your general purpose machine learning force field is for every one of those orbits. And what you realize is that on average, it can be very accurate, right? This is given by your statistical performance of your model, but there will be some orbits for which the error is basically 20 times larger than the average error on the data, okay? So this means these orbits have particularly large prediction error, and you would expect to have problems when you approach those orbits. So this means that we need to have a way to have this, and I think we heard this already for the Grace method, right? Where you have uncertainty quantification, which is based on basically you embed in space or this graph representation, and this is really, really important, right? So what you would like to do, ideally, is to flatten this curve, right? And have a good representation for all the possible orbits of every atom in your data. Second thing you need to do, this was mentioned by Klaus as well in the talk, is do not trust black boxes, okay? We need the black boxes, right? Because the problem we are trying to solve is very complex, right? But it's not as complex as what LLMs are trying to solve, right? So if you look at the most efficient and applicable general purpose machine learning force fields, they have few millions of parameters, right? It is still a black box, but it's not a trillion parameter model, right? Like the biggest LLMs that we have today. So we are somewhere in the middle, right? And so we would like to actually understand what those black boxes do. I think Gabor told you very nicely that if you take some of the bigger models, right, and you just try to compute dimer energy curves, you get nonsense, right? You don't want that, right? So this means you need to have a way to analyze what these models predict for different situations and how do they do this prediction, right? So we have developed this approach based on explainable AI. So together with Klaus's group, we basically benchmarked it on different data sets. And what we have observed basically is that the machine learning force fields do obey some of the principles that we know from chemical intuition. For example, they do predict that interaction strength is atom type dependent, right? So you have different interactions, stronger interaction between carbon-carbon than you would have between carbons and hydrogens, for example, right? So this is something you expect from your chemical intuition, and this is something you do obtain from the models, from the machine learning force field trained on certain data. You also see that intensive properties like HOMO, for example, energy level, is harder to predict, right? You need large interaction range to predict electronic properties. This is something you would expect from chemical intuition, and this is something the models also tell you directly when you apply this explainable AI methods. Something that we do know as well is that interaction strength, so basically the strength of the interaction is a function of the distance between atoms, should follow a power law. Now this power law can be very complicated. There's just one power, right? It can be a sum of many, many different powers with certain coefficients that are geometry dependent, right? But if you actually analyze the models, then you observe exponential decay, of course, right? Because that's how the models have been designed, right? They have an exponential decay. So they don't reproduce something like an r to the minus 6 decay, for example, right? So that's wrong, clearly, right? That needs to be improved, and that's why we are actually adding electrostatics and dispersion by hand at the moment. Hopefully in the future we don't have to do it. Now the other thing is, so this is not, right, the models do not obey the correct decay, right? So they don't follow this physical chemical intuition that we have. The other thing that we know from chemical intuition and from physical intuition as well is that the interaction is many-body, right? So you cannot basically define a simple interaction as just a function of distance between atoms, right? Otherwise quantum mechanics would be boring, right? Quantum mechanics is much more interesting, and this means that at every distance between two atoms, the interaction has some scatter, right? And that's what you see actually, right? So if you analyze a machine learning force field for a certain molecule, for all the different conformations, let's say of a peptide, you will see that the interactions actually do scatter. And the scatter actually can grow with system size, the system size and this distance between atoms. And that's what we would actually expect from our physical intuition, and that's what the machine learning models are telling us. So this is okay, right? They're not doing too bad. So just give some idea of how we do this. So basically, you input your molecule, right? It's a graph. You have a machine learning model. You do a prediction, and then what XAI does is basically your input are positions and charges of atoms. So what you can always do is you say you have two atoms, I and J, they have certain charges, and you propagate all the information. You do all the walks through the neural network that go from atom I to atom J, and then basically for each walk, which can be many, many walks, you can do this, you can return, right? You can go back, right? There are many different ways throughout the neural network, and for each of these walks, you can compute the weight, right? A weight of that walk. And then what you do is you basically statistically do this. You compute weights for each walk, you sum over them, and this basically gives you a contribution of atom I to a prediction of the property on atom J, for example, the force on atom J. So that way you can actually decompose interactions, okay, either energies or forces. If you do this, you realize something interesting. So let's just say that we change the size of our model. So we will change the depth of our neural network. Okay? So in this case, we are using Payne neural network. This is an equivariant graph neural network, one of the first ones that appeared. And what we are doing here from left to right is here on the left, we have one layer model, one message passing layer, right? So it's a shallow neural network, sorry. Here we have 2, 3, 4, and 5 layers, right? So here we have a deep neural network. And then we are computing for this molecule. This is alanine tetrapeptide. We are computing the contribution of atom I to the force on atom J, right? And we're decomposing it as a function of the distance. And what you see is that for shallow model, the interaction decays first. This is correct, right? The chemical bonds are the strongest ones, so you would expect decay, but then it plateaus as a function of distance. This is nonsense, right? It shouldn't happen. I mean, we know that interaction should not plateau, right? On the other hand, if you take the deepest model, so 5-layer model, you see something completely different. The interaction decays. It decays exponentially at the end, as it should. But then, if you, for example, look at a distance of 8 angstrom, you will have atoms. You have many atoms separated by 8 angstrom, right? Because this molecule does something like this. So some atoms are close, some atoms are far. So there will be many pairs of atoms at 8 angstrom. You realize that the interaction at 8 angstrom can change by 5 orders of magnitude. This is complete nonsense. So you wouldn't expect this from your physical intuition. You should expect some scatter, but not 5 orders of magnitude scatter. So in fact, if you take this 5-layer model or a 1-layer model, you run molecular dynamics with these models, they break. The molecules break, right? Because they're very strong forces at large distances, and this makes chemical bonds break, right? And it shouldn't happen, right? So by the way, I did say, but all these 5 models have the same statistical performance. If you look at your statistical errors, they are all the same. They are all great models, right? They predict the energies to 0.1 kcal per mole compared to DFT data, and forces to 0.3 kcal per mole per angstrom, right? They are great, right? If you look at those numbers. But clearly they are doing something wrong, right? So you should be very careful about, someone, a big company giving you a 12-layer model and saying this is a universal model, right? It's probably not, right? Because you actually have to analyze what's going on in the model. And so basically the truth is somewhere in between, right? If you take a 2 or 3-layer model, which is what everyone is using, right? I mean, Maze has 2 layers, we have 2 or 3 layers, depending on the model you use, you see that the behavior sort of is much better, right? Of course, the decay is finally exponential, but it approximates a polynomial at finite distances, and the scatter that you get is actually sensitive. And here you see how, the scatter as a function of the distance, basically we call this many-bodiedness, right? Because this is a deviation from a pairwise behavior, and you see that it basically explodes for a 5-layer model. The 1-layer model is completely wrong, and the 2, 3, 4 layers are actually somewhere we would expect the interaction to be. We don't know what the correct curve is, right? Because quantum mechanics doesn't tell us directly. So that's something we actually analyzing, and there's a recent preprint where we discuss these things, right? But this is something we don't actually know from chemical intuition, what the many-bodiedness should be, right? Is it 2 orders of magnitude, 3 orders of magnitude, 4 orders of magnitude? Who knows? Okay, now, intermolecular interactions. There's much more work to be done on intermolecular interactions, okay? So here are some plots generated by Akil, who is in the audience actually. So we took different models, right? MACE, OMOL, UMA, MACE polar, and solar. So, and we took different types of systems. Hydrogen bonded systems, electrostatic bonded systems, dispersion bonded systems. So this is water-water. Okay, so yeah, so great behavior, right? MACE, OMOL, UMA. But then of course you have a cutoff, right? You hit a cutoff, you go to 0, right? Now it looks like this is a small error, right? But in your simulations, you don't have to add 2 molecules, right? You have many molecules. So this error will accumulate and will give you all sorts of problems. Now, MACE polar for hydrogen dimer, for water dimer, sorry, fantastic, right? It reproduces the data, it's all great. Solar has a bit of a problem, right? You see that when you hit the cutoff of the first cutoff, right? The cutoff that you use for single layer, you have a bit of inconsistency, right? You have a kink here. So again, it's not a big energy change, right? A big energy error, but that must be fixed, right? Clearly. Now let's look at dispersion bonded system. Benzene, benzene, right? Bistacked. Again, MACE, OMOL, UMA, some issues start appearing, right? You see much more problems here. You actually have derivative discontinuity, right, at some point, right? So this is pretty bad, right? So don't use this on dispersion bonded systems, right? This will give you many problems. MACE polar, it has no dispersion term, right? So it becomes repulsive actually between 5 angstrom and 6 angstrom, right? And it actually decays to 0 from above, right? Instead of decaying from below. That's just because it doesn't have dispersion term, right? It's great for electrostatics, and in fact, this repulsion is an electrostatic repulsion, right? That's what you see here, right? So pretty bad, right? That's why now you add in dispersion, right? Solar, much better, right? It is perfect, right, essentially. So you see you have different issues for different models, right? Some models give you better results for dispersion interactions, some models give you better results for hydrogen bonded interactions. So we are not there yet, right? We have all different issues, right? And now these issues will give you unpredictable issues in your simulations, right? Sometimes you will not even see them, right? Because things average out and everything is fine, but sometimes you will see huge effects on your simulations, right? So you have to be aware of all this. Okay? This is unpublished, right? But I thought I showed this to you because this is important to know. You go to larger systems. This is the work of Alex, who is also in the audience. You get much bigger problems. So this is simple molecule, right? Heteronuclear molecule. So you have some electrostatic interactions, you have some dispersion interactions, adsorbed on graphene. What we are doing here is just moving it, right? We are computing the absorption energy as a function of the distance. You get completely different results from different models, right? Now the interaction is much stronger here, right? Benzene has a 3 kcal per mole interaction. This has 14 kcal per mole interaction, right? Because you interact with all the graphene atoms. And so the DFT result here is gray, right? This is the gray curve. This is what happens if you add EVAL to your, so long range electrostatics to your model. Completely wrong, right? This is what happens if you do just Socrates, right? If you do just MACE will be the same thing, right? MACE Socrates give you the same results. And then only if you had multi-scale interactions, I will not talk about this, you can ask Alex or read the preprint, which is here, you actually get the right result, right? And it looks pretty good. So for large systems which have many interactions, right, message passing is not enough, right? right? So doing a local expansion in terms of body order and then doing message passing like we do does not work, okay? Also, there is a recent model called range from Cecilia-Clementi's group. Doesn't work at all, right? It's a bit better than the underlying Socrates model, but it doesn't work, right? It has an electrostatic bias. Basically, it thinks that all the long-range interactions should be electrostatic-like, and in this case, this is not correct, right? You have strong dispersion interactions, and you have strong polarization interactions, right? And so this breaks down, okay? Okay, now, how do you actually look in more detail at long-range interactions? Well, so let's look at bigger system. Let's scale the system size. So this is polyalanine. This is 15 residues. It's the same system where Klaus showed you the molecular dynamic simulations. And so here you have different conformations. You have folded state, which is an alpha helix. You have 3-10 helix. You have unfolded structures, right? So in order to understand interactions, one way to do this is to compute the Hessian matrix, right? So the Hessian matrix gives you the change of the force on atom I to a displacement of atom J. Now this is only a second order approximation, right? But at long range, it's exact, right? Because that's all you have at long range. You only have second order effects, right? So for atoms which are separated by a large distance, Hessian matrix gives you all the information about how atom I interacts with atom J. So that's a perfect representation, right? Okay, so now let's look. So the reference results here. So I have a bunch of models, and the reference results are in blue, okay? So this is my DFT Hessian matrix elements. And the black curve is the mean, the average of all those, right? So you see that there's a lot of scatter in a Hessian matrix, and the scatter actually grows as a function of distance. Because at large distances, atoms don't interact, fragments interact, okay? So it's a scalable effect, right? So this is pretty clear from the reference data. And of course, if you apply normal Socrates, it can only describe interactions up to about 10 angstrom, because you have a 12 angstrom, right? Because you have 4.5 cutoff, for every layer, you have 3 layers. So you describe interactions and then you decay exponentially. If you do maze, you'll have the same thing, right? Now you can try to extend the range of the interaction of each layer to 10 angstrom. But it doesn't help too much, right? It helps a little bit, but you still decay. By 15 angstrom, you decay, because you don't propagate information. Message passing is mean field propagation, right? It does not describe all the important interaction effects. You can make 9 layers, right? Which is what method did, right? Still doesn't help, right? You can include EVI, right? Long range electrostatics. Kind of better, but you still get some strange effects in the long range, right? You can use the range model of Cecilia-Clementi and Frank Noel. Completely wrong, right? Because it has an electrostatic bias. It thinks that all long range interactions are electrostatic-like. This is wrong, right? This is not correct physics. Solar, way better. Because it has long range dispersion effect, so you see it's much better. Muse is basically perfect because it does not put any physical model on long range interactions. It just extends the range in a multi-scale manner. Now let's go to unfolded state. So this was folded. This was a compact state. Now unfolded state is really big. You have distances now up to 60 angstrom, right? In this case, you have distances only up to 25 angstrom, okay? Here you have distances up to 60 angstrom. Now that's a complete disaster, okay? You see here's the reference data, here is the decay, right? All models fail, except Muse, right? So range, again, awful. Socrates now starts failing, right? Because basically it predicts now that electrostatic interactions dominate at this distance. You get this plateau, this harmonic plateau here, which we actually don't fully understand at the moment. We are working on this. But you see it becomes wrong now, right? And only if you have a multi-scale representation of your interactions, you actually can describe them until about 45 angstrom, and then you'll also start decaying faster, right? Because you still have some effective kind of. So big systems, big troubles. Okay? You can ask, but these are small effects, right? I mean, this is 10 to the minus 3 kcal per mole per angstrom. But if you just integrate how many interactions are there, they scale the system size, right? The larger the system, the more interactions you will have at that distance. So that means they will become important eventually, right? Because once again, what we are doing in machine learning force fields, we had electrons, right? Electrons are that do the action. We coarse grain them to atoms, right? But this is not everything. at some point we need to, of course, go into fragments, right? Because what interacts, again, are fragments, right? These are density polarization effects, right? And they are frequency dependent, so they are very long range, they have quite many body nature, right? And this is what you see from your reference DFT plus MBTD. Okay, so there was some good news, there was some bad news, right? I'm pretty much done, yeah. But I think, you know, I don't want, I'm a very optimistic person, right? So I thought, you know, still I have to play the devil's advocate because there are many unsolved problems, right? And there are many hidden problems, and we will only see them in publications that will appear in the next few years, right? We only discover these challenges by doing applications. And I think that's why, you know, the community is important, you guys are important. I fully agree with Gabor that as a community we need to have a roadmap that would allow you guys, right, that are much younger than us, to actually make those important contributions, to do applications, to discover challenges, and then to push, you know, next generation of real general purpose machine learning force fields. Our goal is huge, right? The payoffs are very big. It's not just work for one group, right? It's not just work for 3 groups. I think there's work for many groups. And I think, again, this field is standing now at the exponential wave. We had a few exponential waves, but I feel this one is even bigger because the promise is wonderful, right? The promise is that we will really have a universal quantum force field that is efficient, right? That is accurate, efficient, scalable, transferable, and hopefully also insightful, right? We aim to cover molecular materials, chemical spaces. We had talks, right, by Yuri, by Gabor, by many other people that basically said, okay, these models can treat materials, these models can treat molecules. You know, we want to put all this together. This is quite a big task, right, to accomplish. As you have seen, we have not yet covered real long-range interactions, right? This is a problem. We are starting to do reactivity, but it works sometimes, it fails sometimes, right? There's many experimental data, right, that we can basically compare to, which we haven't compared. And I think we should not be afraid as a community to point out challenges, right? My point to you would be, you can always frame a challenge in an optimistic way. That's why it's not an issue, it's a challenge, right? So this is a discussion I have with people in my group. They come to me and they say, I have this issue. I say, no, you don't have an issue, you have a challenge. Because if you formulate it as a challenge, you can try to solve it, right? Which means that you can progress, right? And so I think you should be very motivated to point out challenges and also push the developers, right, of these methods or contribute to the development yourself. I think this is really the most important thing we can do. This is even more important because there are now many startups and companies that start to work in this field. There's a lot of money that is being put here, and I think it's important for the academic community to define the standards, right? Because when money is involved, sometimes standards become sort of ignored, right? And so I think it's up to us to actually define what the standards are and how you actually, you know, publish the data, how you present it, and how do you point out challenges in every paper that you do, right? So that's my final message, and thank you very much.
Questions? Like 3 or 4.
Yes, thank you very much for a nice talk. When we talk about when there are talks about DFTs not enough, people usually report, okay, we need to recover better the dynamic correlation with couple clusters, right? But what about the static correlation, the multi-reference methods?
So I think for a lot of stuff we are trying to do, we don't really need static correlation, in a sense that, for example, chemical reactivity is not about breaking bonds and then making atoms go to infinity. It's all about rearranging bonds. And for that couple cluster, CCS differences T is good enough, right? Now, if you're now talking, of course, about optical excitations, right, then it's a completely different ballgame. because there you will need static correlation effects. You always have to go beyond couple cluster, right? So there are areas of application for which you will need to address the static correlation question, right? Yes, you are right. But I think for a lot of things that we are now doing in the ground state, that's not the biggest problem we have. I think dynamical correlation is a much bigger problem for now.
Great. Someone else?
I think there was some question.
No, there were a lot of applause, but
I think there's someone said raise their hand.
no, I don't see any.
Oh, here, I saw that here.
I think they were just applauding. So there's a question online appeared now. So future ML force fields will require explicit physical models for long-range interactions, in your opinion?
You know, the fundamentalist person in me says yes, but I think from the evidence I see, I do think that finally we will move away from physical models. That's my prediction. But for the next few years, I think we have to stick with physical models, right? And hopefully then we come up with sufficiently flexible multi-scale architectures, right? That I think we'll learn everything at all scales. And then we need just more data, right? Perhaps they will still follow some of the physical intuition that we have, right? I mean, so I think we will incorporate some physical priors in the models, right? That I think we have to do. So this, in the same way as what we did for the, you know, for the angular momentum expansion, right? And then so on. I think if we ran graph neural networks, it's a lot of physical priors. And in the same way, we have to understand a bit of physical priors for long-range interactions, and they will be incorporated. But I think in the end, the data will take its way, and hopefully we don't have to just add, you know, Leonard Jones-like potentials, right?
Other questions?
So thanks for the nice talk. Basically, it's more of one opinion, but you mentioned that usually people do their force fields for one application for another, and one of the goals will be to unify somehow these and have like a single universal force field, right? For example, when we think about periodic systems or molecular systems, we know that the rules that we use to play with them are different, right? So, like, in your opinion, like, is it really possible to have a single universal force field that works for everything? Or?
Yeah, I think it's definitely possible. It's challenging, but it's, yeah. I mean, the models we have now, Maze, Solar, they all work for periodic and for finite systems, right? There's no problem with periodicity, right? I mean, periodicity is easy to incorporate. You just do minimal image convention, and that's it. We still have cutoffs, right? So, you know, when you do DFT periodic calculation, you have k-point dependence, right? But we do large enough systems that gamma point is enough usually, right? So, yeah. So I think that no, it's definitely possible. But the challenge, of course, you know, how do you actually scale in chemical space, in compositional space, in configurational space? These are different issues, right? I mean, we followed the path of doing biomolecular systems to restrict the compositional problem and to actually address the structural problem, right? The configurational problem. Some other people focus more on the expanding, you know, all the periodic table, but then only doing basically local chemistry, right? So I think at the moment, I do agree that there's like different pathways, different ideas, different models, and that's great, right? I think it's good to have this playground. It's like in DFT or in wave function theory, I don't think there will be just a universal model, right, that everyone will use. I think there's space for several models, right? Some of them will die, some of them will, you know, become stronger, right? And it's great. I think having competition is important in the field, right? I think it will converge and diverge, right, at points in time. But I do think it's possible to go towards a universal model that does both materials and molecules, right? The question is, do we agree on the level of theory that we need to do that? Level of DFT, or, you know, I mean, we don't know. Couple cluster is not applicable to metals, right? For example, right? You wouldn't trust couple cluster there. And so, yeah, it's all about coming to some agreement that people say, yeah, we agree this level of theory is okay. We can use it for both molecules and materials. And then you make a model for both molecules and materials.
At the end, it sounds not only like a jump in the field, but like in chemistry in general, trying to unify both things, right? So let's hope we get there, right?
I think we are working towards that goal, yeah, definitely.
Yeah.
Okay, time for the last question.
Was there something else online?
Thanks, Professor. We have one more question, yeah. So from Sergey Ortiz, regarding biomolecular reactivity, what is your future perspective on combining traditional molecular mechanics and MLFFs, MLMMs?
I think, I think that machine learning force fields are becoming so efficient that I think they're killing QMMM. Right? I think I don't see why you need QMMM anymore. Because it's a kind of worms, right? I mean, the connection between the QMMM part is so complicated, there's just so many ways to do it that it's much cleaner to do a single machine learning force field, right? That's my own opinion, but I know many people are working on QMMM methods, and that's fine, right? Or MLMM methods, right? And that's fine. But I do think that the future is really in a clean machine learning force field.
We have one more question from Tkatchenko. So application question, can I use Solar with classical models such as T3P or SPCE?
Yeah, you can, all right? But I don't know why you would. I mean, it's possible to couple, so it's possible to embed, right, a machine learning force field in a classical environment of charges, for example. But then usually you would need the feedback effects to have polarization of the classical environments. That's also possible, but that requires some development. And I think that, once again, right, the efficiency of Solar is such that I would say that you can just do explicit water in Solar, right? I don't see why you would combine it with T3.
Okay, so we thank Alexandre for presentation.